On a direct technical level, this talk will be related to all the talks of today's morning session. But in spirit, it's also very much related to the very first talk of this conference. We will not be interested in this talk in consistency matters and formal systems. However, what is similar to the very first talk is that I want to share a certain perspective. A perspective which gradually built up over the last couple years in at least the minds of Alexander Oldenziel, my co-author, and myself, and which really came to fruition the last year, prompted by the conference in honor of the birthday of Helmut Schichtenberg. But on the level of like actual technical results, this talk will be rather shallow. Yeah? So all the actual results I will present are either already well known or very simple. The point of this talk is to present a certain perspective. To give you something more to like look forward to, here are four questions which have already been studied again and again from many angles. Several of you have written several papers or indeed even books about one or several of those questions. I will, to the long list of possible ways to look at those questions, I will just add one more. The questions are, why is it that the inductive revolution has been so powerful? Why is it that proofs using Zorn's maximals ideals work so well in constructive commutative algebra where we don't have Zorn's lemma available? Why is it that an element of a ring which is contained in all of its prime ideals is not necessarily nilpotent in constructive mathematics, contradicting Krull's theorem, which would state exactly that? And how can we extract computational content from classical proofs? So these are just like four guiding questions. The partial answers will be given later. For now, I would like to start in a very basic manner by considering an infinite sequence of natural numbers. It starts out like that, 7, 4, 3. And right now, this sequence is not yet visibly good. Also now, it's still not yet visibly good. However, now it is visibly good. And it remains so when later terms of that infinite sequence are getting revealed. An infinite sequence of natural numbers or of elements of some other preorder is called good if and only if some earlier term in this sequence is less than or equal to some later term. Yeah, and the sequence which you saw at the very top of the projector, that was an example for a good sequence of natural numbers. In fact, every infinite sequence of natural numbers is good. There are a couple of proofs of that fact, a couple of constructive proofs, a couple of classical proofs. Let me present one proof which quickly gets the job done. Appealing to the transfinite, appealing to the strongest principle of omniscience we have, appealing to the law of little middle, we know that among the infinitely many terms of such an infinite sequence of natural number, somewhere there will be a minimal value. Let's call that alpha of I. And then for sure, alpha of I will be less than or equal to alpha of y plus 1, because alpha of I has been the absolute minimum value. If we want to abstract from this very concrete situation regarding naturals, then we obtain the notion of a well preorder. A preorder is just a set equipped with a binary relation which is reflexive and transitive. And such a preorder is called well if and only if every infinite sequence of elements of that preorder is good. And the theorem above can be recast in the language of well preorders by saying that the preorder of natural numbers with their usual ordering is indeed well. The notion of preorders is quite important, for instance, in theoretical computer science, where we use it to study termination behavior of algorithms. And it enjoys a couple of stability properties. For instance, if x and y are both two well preorders, then we can form the Cartesian product with the component-wise ordering, and this will again be well. This is a statement known as Dixon's lemma. Similarly, the set x to the star, the set of finite lists of elements of x, equipped with a certain embedding relationship, embedding ordering, will also be well again. That's called Higgsman's lemma. And also the set of trees of a certain kind labeled with the elements of x will also again be well. That's called Kruskals tree theory. Quick question to the audience. How do you feel about this definition of a preorder being well? Say it again? Okay, yeah. I'm also, each time I'm dealing with that, slightly disturbed by that fact. Do you also have mathematical feelings on this definition?
You mean logical feelings?
Yeah, logical feelings. Do you have one?
No, I have none. It's equivalent to many other definitions I use.
It's equivalent to many other definitions, right? There's a whole variety of equivalent definitions, yeah? But how do you feel about this one?
Don't like it.
You don't like it. As constructive mathematicians, we dislike many definitions. For instance, we would definitely dislike the following definition. Preorder is well if and only if no infinite sequence is not good. We would surely dislike this contrived negative formulation of the definition, right? But you also dislike this definition, even though it has no negations in it?
Yes.
Yes? Why so?
It mentions the natural numbers.
Yeah, okay, it mentioned the natural numbers. For the purpose of this talk, let's agree that it's okay to name the natural numbers.
Doesn't contain the proper information.
Doesn't contain the proper information, yeah.
How far do you have to go?
Yeah. Indeed, yeah, there are no witnesses here.
It's not provable for the natural numbers.
It is provable for the natural numbers. Just for fun, I decided to present you an offensive proof, but I wouldn't have to. I could also have presented you one of the couple very nice, straightforward, elegant, constructive proofs. So one indication that the notion might not be the correct one is that those stability results are only available in a classical meta theory. And there are several ways how you can think about this state of affairs. One is that it's not really an intrinsic definition concerning x. Instead, it also references functions from n to x. And this collection of functions very much depends on your foundation you are working in. Like perhaps you're working in recursive mathematics where you only have computable sequences. Perhaps you're working in some topological model. Perhaps you're working in set theory or type theory, but which functions exist also depends on assumptions on which large cardinal axioms or which universes you have at your disposal. A geometric way of observing that there's something odd with that definition from a constructive point of view is that given n and x, there is indeed a space of maps from n to x. However, this space might not have enough points. It always is a space in the sense of point-free topology, but it might not have enough points. But still, the definition presented up there quantifies over all the points of that space. So it's a point set definition, and that's the red flag, even though there are no negations occurring in that definition, that it might not be the most sensible definition. This problem was studied from several persons, and a constructive reformulation was found. I personally learned that from Sylvia Steiler. I think it's due to Thierry. I'm not entirely sure. Here's a constructive reformulation. So let's rename the old definition from well to well star to indicate that we need to read the fine print in order to work with it. Namely, the fine print states that you need to use classical mathematics. And let's have a look at a constructive reformulation. There we first inductively define what it means that some predicate P bars a finite list of elements. The idea is to get rid of those infinite sequences of elements of X and instead only consider finite approximations to those infinite sequences. And then express in a direct inductive manner what it means or what it should mean that every infinite sequence is good in the sense of from above. This is pronounced P bars sigma, and there are two generating clauses for that inductive definition. The first is, if we know that P of sigma just holds, then we may also conclude that P bars sigma. And the second is, if we know that P bars every one-step extension of sigma by one further element X at the right, then we may conclude that P bars sigma itself. We imagine P bar sigma to state that no matter how the finite approximation sigma will evolve over time to a better approximation of some infinite sequence, eventually eventual P will hold. And that's then how we express the notion of well order, of a well preorder, a preorder as well, in a constructively sensible manner, if and only if every, no matter how the empty list will gradually evolve over time to a better finite approximation, it will eventually be good. Good bars the empty list. So that's constructive reformulation. Classically, you can check for yourself that the definitions are equivalent. Constructively, they are not. The definition at the bottom is much, much stronger than the definition at the top. For instance, it does not only apply that every actual infinite sequence is good, but also every partially defined infinite sequence is good. By that, I mean a function, an infinite sequence where at each position n you don't have a natural number. Instead, you merely not have a natural number. Yeah, much, much weaker. There's no way of turning such a partially defined infinite sequence into an actual infinite sequence. But still, if you know that the preorders well in the inductive sense, then you also obtain that every partially defined infinite sequence is good. This raises a couple of questions. One is, what's the origin story of this inductive definition? At least what's a potential origin story which we can just invent irrespective of how it was actually discovered. And the second question is, can we somehow express in more quantitative terms in which sense the definition at the bottom is much, much stronger than the definition at the top in a constructive meta theory? The requirement for these kinds of inductive reformulations appears in many parts of mathematics, and one which you might be much more familiar with is well-foundedness. If you open a classical textbook, then it will say that a transitive relation is well-founded if and only if there is no strictly descending infinite chain of elements, a negative statement. It will be satisfied for the examples we have in mind. However, we will never be able to make good use of it as an assumption in constructive proofs because it's a negative statement, and it's seldomly the case in constructive mathematics that from a negative statement we obtain positive information. It's not impossible, but seldomly the case. The established, or one of the established constructive reformulations of the notion of a well-founded relation is the second one, namely a relation is well-founded if and only if all of its elements are accessible. And what does it mean for an element to be accessible? We again express that by a direct inductive definition, namely an element, namely by this defining clause, to conclude that an element X is accessible, we need to prove that all of its predecessors are accessible. Okay, and then the most crucial property of well-founded relations, namely that we can do inductive proofs with them, is re-established in our constructive theory. Yeah?
You don't really need transitivity for that, do you?
No, not for the definition. Yeah, right. And also, I think there will be a couple of ordinal talks incoming, right? I think they will also somehow flesh that out, perhaps a little bit, give additional background on that. The notions of preorders and well-founded relations are related, for instance, in the sense that given a preorder and given the induced strict ordering, you observe that if the preorder is well, then the strict ordering is well-founded. And here's a quick one-line proof. It's constructive, but refers to the badly behaved notions of well star and well-founded star. Why is it that if X is well star, that then the strict ordering is well-founded star? Well, if you had an infinite strictly descending chain of elements in X, then in particular you have just some sequence. So it will be good at some point, but also it decreases, strictly decreases everywhere. That's a contradiction. The question then is, can we somehow extract from this proof a proof which is constructively less bland, which has more content to it, which actually proves that if X is well in the strong inductive sense, then that strict ordering is well-founded in the strict inductive sense? The answer is we can, using several approaches. I will present one approach in the second part of this talk. Any questions right now? Okay. Let's have a look at one more motivating example. So this talk will not be a talk about well-foundedness or about well-preorders. These would also be interesting topics to talk about, but that were just, for the purposes of this talk, these were just motivating examples. Here's another. It's an example from commutative algebra. Let M be a matrix, specifically a matrix which has more rows than columns. So it's a thin matrix. And assume that the matrix is surjective, by what I mean that the induced linear map is surjective. Then already reading only up to this point, you will already feel some discomfort with that situation, because you learn in undergraduate linear algebra, where we work over fields, that such a situation is not possible. Over fields, there cannot be matrices which have more rows than columns and are still surjective. For a matrix to have any chance of being surjective, it needs to be square or have more columns than rows. But this kind of situation is impossible. And what the theorem is telling us is that for arbitrary rings, by ring I mean commutative ring with unit, we have the same situation. There's just one ring over which this situation can arise, namely the trivial ring in which 1 equals 0. The statement that 1 equals 0 is, from the point of view of ring theory, almost as good as the true absolute logical bottom. Yeah? So from that statement, almost any ring theoretic property of the ring can be concluded. So this theorem is telling us that more or less exactly the same situation holds as in undergraduate linear algebra over fields. There are a couple of proofs of that theorem, very nice constructive ones, very nice classical ones. Let me present to you the textbook proof of that. If you have the misfortune of opening some random textbook on algebra and not the beautiful book by Henri and Petit. The proof starts out as follows. The proof says, well, assume not. Then 1 is not equal to 0 in the ring. And hence we might remember that there is a maximal ideal, because it's a theorem in undergraduate commutative algebra that non-trivial rings always have maximal ideals. Here's a quick reminder of what a maximal ideal is. You see here a chart of all the finitely generated ideals of the ring of integers. At the very top, you see the unit ideal, the set of all multiples of the number 1. At the very bottom, you see the 0 ideal, the set of all multiples of the number 0. And in between, you have many more ideals, set of multiples of the generator in parentheses. The ideal at the very top is also called improper. It's the unit ideal. And all the other ideals are called proper. And by definition, an ideal of a ring is called maximal if and only if it's maximal among all the proper ideals of the ring. So all those rings, all those ideals generated by prime numbers will be maximal in the ring of integers. What's so useful about maximal ideals? What's useful about them is that if you mod out by such a maximal ideal, you obtain a field. For instance, Z mod 2 is well known to be a field, the smallest field, the field with second smallest field, the field with 2 elements. So therefore, they are nice for reduction techniques, because you observe that the matrix is still surjective when you pass to the quotient ring A mod M, but then also A mod M as a field. Hence, you have a contradiction to undergraduate linear algebra. Hence, you are done with the proof. I really like this proof in a certain sense because it's very short, very memorable. It's a very quick reduction to the field case. However, of course, it's also extremely offensive because the statement of the theorem is very concrete, very clear. It deals with matrices. The conclusion can be stated as an equation. The hypothesis can also be stated as a couple of equations, one for each dimension, but still the proof appeals to the transfinite 2 times. So of course, we should be challenged, we as logicians, to present better proofs, or even to extract from this given proof a constructive proof. And this has been done, and this has been analyzed by several people using several techniques. And again, the perspective I will present in the second half of this talk will yield one more perspective of constructivizing this given proof. This proof contains 2 appeals to the transfinite. First in the very beginning with the assume not, and then with the maximal ideal. In undergraduate mathematics, you learn that you need that you need Zorn's lemma in order to come up with maximal ideals. The first appeal to the transfinite, the assume not, is actually not that much of an issue here. One reason is that you can just slightly redefine the notion of a maximal ideal, taking care to define the notion of a proper ideal more carefully, and then every ring will have a maximal ideal, including the trivial ring. So that's not so much of a problem. Also, we know that there are general techniques for eliminating any usage of the law of excluding middle from classical proofs. So the actual issue is the existence of the maximal ideal. So let's have a look at that. Given a ring, is there a maximal ideal? Here's what we know about that. Firstly, if Zorn's lemma is available, then yes, there is a maximal ideal. That's one of the prototypical examples of how you can use Zorn's lemma. It will quickly concoct a maximal ideal. It might not surprise you that constructively we can also obtain a maximal ideal in the case that the ring is countable and that we also have a membership test available for checking whether some element belongs to some finitely generated ideal. Because in that situation, we can just build up the maximal ideal in stages. So we line up all the elements of the ring in an infinitely long row, and then have a look at all the elements in turn. And we build up the maximal ideal gradually, starting with the 0 ideal. And then we just keep adding elements to our ideal under construction, but only if doing so would not cause a blow up, if doing so would cause the ideal to become improper. That's the construction. It may surprise you that in constructive mathematics, we can in fact also drop this decidability condition. For arbitrary countable rings, we again can construct the maximal ideal in stages. This time we cannot carry out this case distinction, but we also don't need to. We just write down this singleton set, the sub-singleton set, the set of all those elements of the ring which are equal to xn, the next element in this long row of all elements, with the extra condition that adding xn to the previous stage would not cause a blow-up. Without a membership test, I cannot tell whether the sub-singleton set on the board is empty or whether it's inhabited. but still it's a perfectly fine sub-singleton set. We can take the ideal generated from it, the set of finite linear combinations of elements of it, and add that to Mn. And this way we obtain a maximal ideal in A. This construction is due to Krivine, and it has also been explored by Berardi and Valentini. And they wrote on the right, in respect to this construction, that it's non-informative, because it's like infused with all those negations and with those non-detachable subsets where we cannot actually know whether an element isn't contained in that or not, so that they concluded that while formally on paper they are indeed maximal ideals, that we cannot use them for anything. Peter Schuster and I were quite surprised when we analyzed this construction with perhaps fresh eyes, and then noticed that indeed this construction is enough to give constructive proofs for several well-known test cases in constructive commutative algebraics. In particular, the example with the surjective matrix can be constructivized by using exactly this maximal ideal condition, in the case that the ring is countable. Another expert on these matters even commented that this construction is a bad joke, and I agree, it's totally a bad joke. It's a sleight of hand in some sense, but still it's a sleight of hand which somehow works and in the end gives concrete computational content. If the ring is countable. What if the ring is not countable? What if the ring is just a general commutative ring with unit? Well, then the answer is that, I'm sorry to say, there just might not be a maximal ideal. You cannot constructively prove the existence of a maximal ideal. And also more concretely, you can write down models of constructive mathematics where you can just check that there is no maximal ideal. However, it turns out that even though there might not actually be a maximal ideal, the first order consequences of the assumed existence of such a maximal ideal actually do hold. So if all you're interested in at the end of the day are first order theorems about surjective matrices, for instance, then you might just as well pretend that your ring has a maximal ideal. It doesn't really, but it behaves as if it would from the point of view of bounded first order formulas. Question is, why is that so? How to make sense of it? And with that, we will start the second part of this talk, culminating in that introduction of new modal operators for constructive mathematics. But before that, we will have a short summary of topos theory, to be more precise, Grothendieck topos theory. And just so that we are all on the same track, let me stress the following. For the remainder of this talk, we will not actually need topos theory. We will not actually need category theory. We will also not need the category of all sets. We don't need any set theoretic foundation. What I will present in the remaining part of the talk will in fact work in most foundations. I haven't checked everyone individually, and also there are issues in homotopy type theory when we are dealing with higher types, okay? But in most, let's say one categorical kind of foundations, what I will present will work. So if you have the idea that Grothendieck topos theory is fixated on some category of sets, then please try to lose yourself from that idea, yeah? Because it's false in a certain sense, and the category of sets will not appear. Also, the notion of what a sheaf is will not appear. What will appear instead, tackling these questions, is the notion of a forcing notion. So recall in the very beginning, we approximated infinite sequences by finite approximations, by finite lists. And this idea of approximating infinite objects by finite approximation is a very powerful idea, and it appears in lots of contexts in mathematics. And one way to formalize it is using the notion of a forcing notion. A forcing notion is a preorder equipped with a certain covering system. And for every forcing notion, we can have a look at its filters. Let me present a couple of examples. For instance, if we want to approximate maps from n to x, where x is some set, we can use the preorder consisting of all the finite length lists of elements of x, x star. The purpose of that covering system is to specify which kinds of refinements we are prepared to undertake when we notice that a given approximation doesn't quite cut it. And the kind of refinements we allow ourselves in that first case when we want to approximate maps from n to x is that we extend a given finite approximation by one more element called lowercase x on the board at the right. We might also try to approximate not arbitrary maps from n to x, but surjective maps from n to x. This is a harder task, especially considering that sometimes there are no surjective maps from n to x. For instance, at least in classical mathematics, there are no surjections from the naturals to the reals. The reals are uncountable, and very famously so. But still, we can try to approximate surjections from n to x in a finite manner by again using finite lists of elements, depicting the first couple values of such a hypothetical surjection. And again, we need to be prepared to carry out certain refinements. Firstly, we need to be prepared to make such a finite approximation more defined by adding some element x at the right. But also, we need to be prepared to make such a finite approximation more surjective by ensuring that any given lowercase a somewhere appears in the finite approximation. And that's the purpose of the second kind of coverings listed there. We could go on and on and on. There are lots of forcing notions in constructive mathematics if you look for them. Let me just mention two more. We can approximate arbitrary ideals by finitely generated ones. Or we can approximate points of a given, let's say, topological space by the collection of its open neighborhoods. Yeah? And the smaller an open neighborhood is, the more precisely it determines a point. What can we do with a forcing notion? The purpose of a forcing notion is to give rise to a forcing extension of the base universe. I picture that as we are doing mathematics in our usual mathematical world, and then we extend that world to a bigger place, perhaps a better place from some point of view. And then we will continue to work in that better place. And at the end of the day, we will see what results obtained in that better place tell us about the base universe in which we actually wanted to work in. For instance, an extension of the universe might be better in that it does contain a surjection from the naturals to our favorite set X, because that is a way of ensuring that any given ring now becomes countable. And then we can apply that bad Joe construction from Krivine in order to come up with a maximal ideal. And then we can read classical proofs making use of maximal ideals in that universe. To work in those enlarged universes, we need this definition, which is similar to the very first inductive definition from this talk. Only this time it will not be about finite sets of elements. Instead of will be about elements of L, whatever the forcing notion L is like. We inductively generate, using two clauses, a predicate P bar sigma by saying, well, P bar sigma if P actually holds on sigma, or we may conclude that P bar sigma if it bars all the possible refinements of some covering of sigma. Again, we imagine P bar sigma, also written in this way, as the statement that no matter how the given finite approximation sigma will evolve to over time, eventually P will hold.
Is there a typo in the last line?
Say it again.
Is there a typo in the last line?
Might be. Where do you suspect a typo?
Sigma as a bound variable and as a free variable.
Yeah, it's not a typo, but an abuse of notation. Yeah, so I think of this expression as in total still having a free variable called sigma. Yeah, and I should more properly write let's say this. Yeah. So sigma is still a free variable. And this states that no matter how sigma will evolve over time to a better approximation, eventually we will have an approximation tau such that p tau holds. However, it's inconvenient to come up with new and new Greek letters for those finite approximation, and hence that abuse of notation to call all of them sigma. If you don't know sheaves, and if you don't know category theory or topos theory, but if you do know the double negation translation, then you will feel right at home at the next slide. The purpose, as already said, of a forcing notion is to give rise to a forcing extension of the universe, a better place to do mathematics in. This seems like a very extreme, perhaps even esoteric or at least philosophical notion, but at the end of the day, it's extremely concrete and computational and constructive and down to earth. I want to actually construct this forcing extension because that would require sheaves, and I want to avoid those. But I will tell you the result, which you can also take as a definition, of which statements are true in such a forcing extension. The idea is that perhaps I will never be on Mars, that planet. However, I can kind of imagine how it might be to live like on Mars. Similarly, we are trapped in the mathematical universe we are currently working in. However, using what is called the Napa translation, we can somehow gather how it would be to live in V to the Napa, some forcing extension. Namely, a statement is true in the forcing extension if and only if actually just its Napa translation is true. So what is the Napa translation? Let me present one example. From that, I hope that you gather the idea, even if I don't present the formal translation rules. In the case that we use this weird one-element forcing notation from before, this Napa from the slide before degenerates simply to the well-known double negation, just the not. And in this case, the Napa translation degenerates to the double negation translation. For instance, the double negation translation of the statement that every natural number is 0 or a successor is then what's at the bottom for every natural number n. It's not the case that not it's 0 or not there's some m such that not n is the successor of m. That is how you obtain the double negation translation from the statement. You just copy the statement, but then include a double negation in front of every atomic formula, such as equality, in front of every disjunction, and in front of every existential quantifier. And if we are working with a different forcing notion, then we will not need we may not use the double negation, but instead the nabla from before. Yeah? And depending on the forcing notion, we will then obtain hugely different kinds of statements, all related to the original one. For instance, and coming back to slide -1, we have the following. Given the forcing notion associated to a space, we might be wondering whether in the forcing extension, the well-known theorem from undergraduate linear algebra holds true, namely that every symmetric matrix has an eigenvector. When we try to determine whether that's the case, we need to carry out the nabla translation to see what this actually amounts to, and then check that statement. And this turns out, after unwinding everything, that the statement that every symmetric matrix has an eigenvector holds in V nabla if and only if, for every continuous family of matrices, locally there's a continuous eigenvector picking function. And that, by the way, is false for most parameter spaces. And that is a quick way how you can be sure that you will never obtain a constructive proof of the claim that every symmetric matrix has an eigenvector. Because if there was a constructive proof, then that result would hold in every forcing extension, because the nabla translation is sound with respect to intuitionistic logic. But there are several forcing extensions in which this result does not hold. Just a side comment, in constructive mathematics we can prove that every symmetric matrix does not have an eigenvector. So this result now actually does hold in every forcing extension. And if we apply that knowledge to the specific forcing extension coming from spaces, we obtain the following fact from, let's say, advanced analysis, namely that given any continuous family of symmetric matrices on a dense open subset, we locally have eigenvector packing functions. So there might be a couple of exceptional points where the task of continuously picking out eigenvectors will not be satisfiable. However, excluding those couple points and still working on a dense open subset, we will always succeed.
One question.
Yeah.
So in the first example, you have double negation built in.
Yeah.
But not in the second one.
Say it again, not?
In the second one, you don't have double negation.
No, that was an actual result.
Okay, so the coverage for the singleton you
Yeah.
gave a coverage that included the double negation.
The once negation, the single negation. The coverage, for example, 1 was here forcing notion number 6 and did not contain a double negation, but a single negation. And the forcing notion number 5 did not include negations at all. Okay, let's try to wrap up and revisit the beginnings of this talk. First, notice that every such forcing extension, which you now know how to work in, even though you don't know how to actually construct it, is unique in a certain sense. Namely, found for V to the nabla is unique in that it definitely contains a filter of L, namely the so-called generic filter, even if in the base universe there are no filters at all. For instance, recall that forcing notion whose filters were the surjections from n to x. There might not be any surjection from n to x if x is uncountable. However, in the forcing extension, we always have such a surjection, namely the generic one. And now these turn out to be important because we have the following observation. A preorder is well in the strong inductive sense if and only if the generic sequence is good. So classically we had this notion of well star preorder as well star if and only if every sequence in the base universe is good. And then we had that better constructive reformulation. And it turns out that we can cast this reformulation again using the notion of an infinite sequence, using the perhaps more evocative notion of an infinite sequence instead of that direct inductive definition using generating clauses. It's just that we need to switch to a different universe. Yeah? So a preorder as well if and only if a very particular sequence is good, namely the generic sequence, which lives not in the base universe, but in some forcing extension. Also, we have the following. An ordering is well-founded in the strong inductive sense, if and only if a very particular descending chain validates bottom, namely the generic such chain. Not all those forcing extensions are created equal. Some are more interesting from the point of view of obtaining results about the base universe, namely the so-called positive extensions and the positive overt extensions. Generally, the statement that something holds in V and that that same claim holds in V to the nabla, these are two totally distinct statements which don't have any implication or relationship between each other. They can mean totally different things. Like with the double negation translation, yeah? A statement usually neither entails its double negation translation, nor is it entailed by it. Yeah? They are just different in general. But for some kind of forcing extensions, and there are very concrete syntactical criterions for that, we do have that the statement that some statement holds in V and that it holds in V to the nabla, that they are equivalent. And then we can define the following modal operators, and these are the new modal operators I wanted to propose. Namely, a statement holds everywhere if it holds in every forcing extension of the base universe. A statement holds somewhere if it holds in some positive extension. And a statement holds proximally if and only if it holds in some positive overt extension. Positive overt extensions are like the best kind of extensions because from the point of view of first order formulas, there is no difference at all between V and V nabla. V and V nabla satisfy exactly the same first order statements. It's just that V nabla might satisfy different higher order statements. For instance, in V nabla, we might have an enumeration of all the ring elements, while in our base universe V, we might not. And therefore, I picture a positive overt extension to be extremely near my current base universe. That's hence why it's proximal, and I'm grateful to Lukas Stoll for suggesting the terminology. In set theory, this is a similar set of modal operators is being investigated for a long time, but in some sense precisely written down 2011 by Joel David Hempkins. And this is the attempt of not exploring the set-theoretic multiverse, but the topos-theoretic multiverse. However, for a totally different reason. The set theorists who are exploring the set-theoretic multiverse are, for instance, interested in philosophy, or they are interested in exploring the range of set-theoretic possibility. Can it be that the continuum hypothesis holds? Yes. Can it also be that it fails? Yes. Can it be that the continuum hypothesis holds and there are also exactly 7 Marlow cardinals? Yes. Can it be that, and so on? Yeah? These kinds of questions are interesting from the point of view of the set theoretic multiverse approach. And Joel David Hempkins has this quote that studying the set theoretic multiverse is like studying the constellations in a beautiful dark night sky. Every star is like a universe of set theory, and then those stars are connected, for instance, because one universe might be embedded in another. the kind of modal study of the topos theoretic multiverse I'm proposing is also interested in those sorts of questions, but not primarily so. My application is to very down to earth to constructivize results in commutative algebra or algebraic geometry. Very, very down to earth. And let me conclude by just giving a short tour of what holds in that modal multiverse of forcing extensions. For instance, we have for every inhabited set, even and especially so if x is uncountable, proximally we do have a surjection from n to x. Correspondingly, using the bad joke from Krivine, for every ring whatsoever, proximally, there is a maximal ideal. Hence, in that overt positive forcing extensions, we also have all the consequences of the existence of a maximal ideal. And because that forcing extension is positive and overt, all the first order consequences pass down to the base universe, which is the only universe I'm actually interested in. The notion of preorders, we had to reformulate it in the inductive sense in order to re-obtain those classical stability results of Dixon's lemma, Hickman's lemma, and Kruskal tree theorem. And I invite you to have a look at the beautiful inductive proofs of those stability results. Besides those beautiful direct constructive proofs, I'm also interested in just extracting from the given classical sequence-based proofs the same constructive content. And I can do using this observation. A preorder as well in the strong inductive sense, if and only if everywhere, every infinite sequence is good. So I'm now reduced to studying actual infinite sequences instead of those inductive definitions. A ring element is nilpotent if and only if it is contained in all prime ideals everywhere. So if you have a ring element which is just contained in all prime ideals of the base universe, it might not yet be nilpotent. But if you also know that it's contained in all prime ideals, in all forcing extensions, then you may indeed conclude constructively so, explicit bounds, that the element is nilpotent. And that statement that let's say that Peano arithmetic and Heiting arithmetic verify the same pi2 statements. That Friedman trick, that continuation trick regarding the double negation translation, that bar theorem can be cast in the following language. Somewhere, the law of excluded middle holds. For sure, it does not in our base universe, at least not if we are constructive mathematicians, but it holds somewhere in a positive forcing extension of the base. So, final slide. Let me give possible answers to those 4 questions. Not answers which are intended to replace the already given answers, just new answers from that multipliers point of view. Why has the inductive revolution been so powerful? That idea of replacing the original definition of well by the new one, and also for well-foundedness and also for Noetherian. Why does it work so well? Well, because the inductive conditions are equivalent to truth in all forcing extensions and not only among the multitude of universes, the base universe. Why do proofs using Zorn's maximal ideals work so well in constructive commutative algebra? Well, because every ring has a maximal ideal, proximally so. Why are elements of the intersection of all prime ideals not necessarily nilpotent? Well, because it wasn't actually the intersection of over all prime ideals, just the one of the base. We forgot the other ones. Sure, if we forget those, intersecting with those, we will not expect Krull's lemma to hold. How can we extract computational content from classical proofs? By traveling the multiverse, upwards to better and better universes, always keeping the tie to the base universe. using observations such that the law of excluding middle holds somewhere, and the axiom of dependent choice holds even proximally. So we can freely turn on lem and DC if we want to. We can also turn them off in case we don't like them. They are switches in the terminology of the set-theoretic multiverse. We can freely turn them on in case we need them, as long as the conclusion we finally want to prove is of the required form. Thank you very much for your attention. That's it.